Swayam Prabha. Digital India. Educated India.
Dear viewers, today I would like to discuss a application area which uses some of the advanced surveying techniques for extracting building attributes from high resolution satellite data. It has been observed that natural hazards such as floods and earthquakes cause widespread damage to urban areas. Many a times it is found that the damage to the building is mainly due to inadequate use of building material or non-adherence of building standards. If the buildings are insured for damage, then large insurance money is to be paid. The insurance companies do not have adequate information prior to insurance whether a building is safe from any impending hazard. To acquire such information regarding individual buildings through ground based methods is going to be time consuming and costly. So, this study tries to highlight the usage of advanced surveying techniques to generate a building attribute database, so that the same can be used for assessing the risk associated with each building as and when a natural hazard occurs. So, the objective of this study is to generate the information of some of the buildings characteristics using high resolution satellite data like QuickBird and benchmarking with respect to ground based data. The study also includes generation of knowledge based rules for creating a building inventory GIS database. The scope of the work can be defined as follows. First, business rule development and calibration. The development of business rules for image classification to extract the building level attributes. Next is building footprint extraction. An in-house technology has been developed to generate independently the building footprints for the above mentioned areas of the two cities for which the study has been implemented. Building inventory generation. Along with building footprints, the following attributes need to be extracted, such as building height, number of stories, complete square footage, footprint square footage, construction class, occupancy type, exterior wall material, building shape, roof geometry and roof material. And finally, validation with field survey data or any secondary data with the help of field survey data or available field photographs of some of the sample buildings. There are three study areas which have been selected, namely Anacenta, Costa Mesa in Orange County and California, and Naples in Florida in United States of America. One site each in Santa Ana and Costa Mesa and two sites in Naples covering an area of 1 square kilometer each has been selected for this study. This slide shows the raw data which has been acquired for QuickBird. QuickBird data is available in two forms. One is panchromatic data at 0.6 meter resolution and multispectral data at 2.4 meter spatial resolution. So, the image on the left hand side is the panchromatic image or the black and white image, and the image on the right hand side is the multispectral data set. The next slide shows the raw data for Santa Ana. Well, in these two areas, predominantly urban area have been selected, so that the impact of the same can be studied, whereas in Santa Ana high rise buildings have been selected, areas comprising of high rise buildings have been selected, so that the extraction of information for high rise buildings can be extracted. Similarly, for Naples area, two sites have been selected. Naples is a area in Florida which is close to the coastal region and is very commonly used by tourists for vacation. So, here there are lot of resorts which we can see, and these resorts may be single story or they could be multiple story buildings which could be there. Another area of Naples is the commercial area, which comprises of both residential and commercial areas. So, for the generation of building footprints and its attribute, a semi automated approach has been adopted. Here pan data has been used as a single data set for extracting edges, whereas MSS QuickBird data has been used for classifying the building material. So, now let us look at the methodology which has been adopted for this study. We have two data sets. First is the panchromatic QuickBird data and the other is MSS QuickBird data. The panchromatic QuickBird data is subjected to different forms of data extraction available through image processing, that is density slicing and Kirsch filter have been selected to extract the information. After the data has been subjected to these processes, the edges are converted from raster to vector. The vector layers need to be cleaned and built for clarity in the information, and subsequently the data set which is available, it has to be converted into shapefile before any analysis in the form of vector based in GIS environment can be adopted. Sometimes a manual editing process may be required if the edges of the building are very wide. So, through manual editing this is resolved and then we start the building characterization. Prior to this, the MSS QuickBird is merged together with the panchromatic data set, because this is at a higher resolution. So, merging of data has been carried out, and through unsupervised classification technique, as discussed earlier when we were discussing digital image analysis of remote sensing data, we adopt unsupervised classification for extracting the building material quality. Having done these, when we are characterizing the building, certain decision rules have to be generated, so that they work as guidelines in characterizing a particular building or a group of building. So, the inputs are then taken from this decision making rule, which is a knowledge based system. Apart from this, some ancillary data may be required, which could be either acquired through internet or through some browser systems which provide information regarding the earth, such as Google Earth, and some of the data which may be provided from ground. So, the ancillary data may be acquired from these sources, and along with the inputs coming from all the four ends, that is the raster data, the vector data and the decision making rules, attribute definition for each building type in terms of occupancy, construction, footage area, height of building, number of stories, roof geometry, rooftop material and cladding material are to be identified. In order to do the processing of the digital images, ADAS Imagine 8.6 version has been used, and for creation of the GIS data layers and database, ArcGIS 8.3 has been used. Our first task is to develop the business rules. In order to do this, we need to focus our attention on the elements of image interpretation. These elements are shape, size, tone, texture and association. So, the first decision knowledge based rule is classification of building types, that is, examine the building shape and size followed by the tone of the object. In order to do this, two sub rules have been identified. Sub rule 1A: if the size of the building is small and its shape is regular, that is either square or rectangular, and the shape of the roof is gabled / slanted or hip roof, then the building will be assigned as a residential building. The same can be seen in the cutout of the image, which shows some of the residential buildings having gabled or slanted or hip roof topping. Sub rule 1B: if the building has a uniform tone and that the adjacent buildings also have the same or similar characteristics, that is, the pattern is same and continuous, the group of buildings would be assigned as residential areas. Here we can see in the center of the image the blue square or regular shapes which are there. These are buildings which are located in a particular area, and these buildings may be one story or may be multiple story. It all depends on the building type, and thus what we can find here is that there is a regular pattern in which the buildings have been laid out, and this gives us a clear cut example that this is a residential area. Sub rule 1C: examine the nearby objects, that is the shape of the roads, location of parks. If the group of buildings occurs on both sides of the road in a regular manner, the group of buildings will be confirmed to belong to a residential category. Additionally, presence of small parks or lawns within the area will further strengthen the confirmation of the group of buildings as residential areas. Sub rule 1D: examine the building size and shape, and if the size of the building is large and on the rooftops many utility items such as water storage tanks or air conditioning units appear, then the building may be assigned as a commercial building. It may be an office complex or a hotel or a warehouse. Sub rule 1E: if the rooftop is flat and the presence of underground ramps or open space for parking having stories greater than 4, the building may be categorized as a hotel or an office building. If the front of the building has lawn space or close to it water pools exist, then the building can be classified as a hotel, or else it is a office complex. The same can be seen here. In the center we find that there is a elliptical shape object which is nothing but the rooftop area of a particular building, but since they are adjoining on the right hand side, we find that there is a ramp which goes below the ground. This gives us a clear indication that this is a hotel area. If the building, next sub rule is rule 1F: if the building height is small with large open space in the surrounding with clear access to road network or loading and uploading areas exist, the building may be classified as a warehouse. Then rule number 2: classification of rooftop building material. Spectrally classify the building and based on the signature, tone and texture classify the building material. So, rule 2A for residential areas: if the building roof is gable, hip, gable and or slanted, and the number of the stories is less than 4, and the building material may be aluminum covered, the building material used may be aluminum overlaid by tiles. If the color of the tiles in the FCC of the satellite appears in the varying tones of red, then it is earthen tiles. If the color tones of the FCC of the satellite images appear in gray, then it is shingle tiles. Rule 2b, commercial areas. If the rooftop is flat and the size of the building is large with open spaces for parking or loading unloading area exist, and the color tone of the roof material is having shades of gray, then the roof material may be classified as PVC fiber mesh with bitumen covered by concrete tiles for waterproofing. The cutout below adjacent shows such a area in the satellite image. Rule number 2b, commercial areas. If the color tones appear as bright or white, the roofing material used may be is concrete with glazed tile. Similarly, rule 2c is general industrial buildings, that is the rooftop material of such buildings will normally be aluminum or PVC fiber corrugated sheets having rubberized bitumen layer overlaid so as to prevent corrosion and also provide waterproofing. The color tones of such materials will appear in the shades of black on the FCC of the satellite image. For cladding material, the residential type of buildings will use plywood or gypsum board with covering of paint/tiles. Warehouses will have precast concrete walls. Hotels and office buildings, it could be concrete/framed aluminum panels having plywood overlain with concrete or glazed glasses. And finally, for general industrial building, the cladding material could be framed aluminum frames covered by plywood or concrete having bituminous covering for waterproofing. It has been observed that remote sensing data is not adequate for this type of data extraction. Having defined the decision making rules, now we start with the actual analysis procedure. First procedure is density slicing. First of all, the image is visually interpreted to understand the shape and size of the buildings. After this, density slicing is carried out. This gives the ability to highlight a range of pixel values in the lookup table. It is one of the common and reliable methods of finding out the optimum threshold value and is done by manual selection. On the basis of visual examination, a threshold value ranging between 500 to 700 is applied. This may be applied on a repeated basis till the buildings are sharply seen with respect to the background. So, the procedure for density slicing is you click on the modular option on the main menu bar of ADAS Imagine, click Spatial Modeler and select the model maker and apply the conditions for the model as shown in this particular slide, wherein the condition has been now applied here into the model maker, and on the basis of this the analysis is carried out, which yields the following result as now seen. So, one can compare that from the original data now we are able to extract by and large all the buildings which are there in that particular area. Some of the lines which are there, these could be due to the presence of such material which is lying adjacent to the road area and have similar spectral characteristics. However, this can be removed subsequently. Having created the raster based information regarding the information, the same has to be converted into a shape file. So, this involves the process of cleaning the data, building up of the vector topology, conversion from coverage to shapefiles. Even after this, the polygons may not be smooth. So, we may have to do some manual editing. So, let us look at the procedure of converting the rastered information into vector information. So, we go to in the ADAS Imagine software, we go to click option on the main bar, select vector utilities, click on the raster to vector option, click on clean vector layer option, click on build vector layer topology option, and then finally, we import the information through the module which is available to us. And based on this, what we find now is that we have been now able to convert the coverage information which was there into a vector information which is now in the form of continuous lines. Having done this, we need to do the cleaning and building up of the vector topology through the process as highlighted here. Since the editing is not possible in coverage files, so this conversion from coverage to shapefile is required. So, for undertaking the conversion from coverage to shapefile, we can go to the import export option and select the required file and go for a shapefile generating option and create the data set. So, after we have performed the density slicing with building edges, now these are in the vector form. So, earlier we were only having the outlines, but now we are having the edges in the form of vector lines. In order to extract the informations which is there, these informations would be primarily in the form of edges, and these edges need not necessarily have a specific orientation. So, we undertake the process of filtering, spatial filtering, wherein curve filter has been selected to in this particular study. This operator is equally sensitive to edges in all the 4 directions, that is 8 orientations. It gives negative weights to each 5 consecutive neighbors and positive weights to 3 of the weights chosen, so that they all sum up to 0. The central pixel can be given a 0 weight. This may be applied on a repeated basis till the buildings are sharply seen with respect to the background. Again, we convert from raster to vector, clean the vector file and convert it into a shape file. So, these slides, as a matter of fact, show the model for curve filter. We have 8 models which are available to us, and on the basis of this, we apply the conditional rule to undertake the sorting of the edges which have been built up from, which can be built from the curve filter. And after applying the curve filter, now what we find is that the edges of different objects have now been extracted very simply from the data set. It may be observed that some of the polygons may have certain amount of thicknesses. So, we may need to reduce these thicknesses by a procedure, wherein we again apply the curve filter and then we manually join both these informations to get the additional building polygons, which can be merged together to provide a complete building footage data set. So, now what we have done is we have thinned the edges and we had the polygons already available through the shape file, and these have been merged together, and what we see is the highlighted areas of the building. Now, in this case, you may notice that the roads which were earlier also appearing as outlines of the edges were seen, the same has now been eliminated. So, the roads and alls in the area are now not going to be present, only the building shape files are going to be available to us. Having done the extraction of edges, our next part is to perform the unsupervised classification. In order to take the advantage of the high spatial resolution offered by PAN data, what we do is, first of all, we merge the PAN and the FCC of the multispectral data, so that this transforms the original satellite data into new bands that express the greatest amount of variance or information from the feature set of the original bands. So, here one can see that the PAN image and the FCC image both together have now been merged together, and the image on the right hand most side is the merged image that we have, and this image is now going to be subjected to unsupervised classification. In order to perform unsupervised classification, IDAS provides a option of ISO data. Well, in this we need to specify the number of iterations and the number of classes, and these have been kept as 25 and 10 respectively. With the help of this classification, the roof material will be identified. So, what we do is, in the IDAS Imagine, we select classifier and go in for classification, click on unsupervised, provide our input data, and based on this, what happens is, it creates the spectrally similar informations which are present on the shape files that we have generated. So, one can see very clearly the type of information extracted in this particular image. Interesting to note that by and large all the building rooftop materials have similar properties. However, there are some buildings which are dissimilar, and these can be seen in the red color. So, classification of the rooftop building material, spectrally classifying the building, and based on the signature tone texture we classify the building material. If the color tone appears as white or bright, the roofing material used may be concrete roof with glazed tiles. If the rooftop material is having shades of gray, then it may be classified as PVC fiber mesh with bitumen covered by concrete tiles for waterproofing. Having extracted the building material or the roof type material, our next step is the computations of the height. With the help of the building shadow, we can calculate the height of the building and the number of floors. Using 16 feet as the standard height of one floor for all buildings, the formula can be used as height is equal to P divided by sin theta. So, this slide provides us the basis of the height calculation. One thing the viewer may note, that in order to find out the height of the building, we need to correctly identify the point, the topmost point and the bottommost point. But what happens is, the bottommost point, since it is lying in the shadow area, it may not be visible always very clearly. So, what has been done is that instead of using the sine rule, the tan rule has been used by taking into consideration the slant height, and thus the building height can be obtained. Having done this, our next task is to generate the GIS database. So, some of the typical parameters of the database are building ID, class of building, shape of building, construction, footage area, height of the building, number of stories, occupancy, roof type material, roof type itself, and the cladding material. So, in order to create the database, we first click the attribute file and open the attribute table. We then select the option and we say add fields, so that the user defined fields can now be entered or created, and after this we get the shape file. So, here within the GIS framework, what we have done is, now we have opened the attribute file for the corresponding data set. We select the different fields which are required to identify the various characteristics which are there. So, we can see that we have the building ID, then we may have the number of stories which are there, configuration of the building, that is the shape, or we can enter for the rooftop material, and so on. The various fields can be added for different attributes. Having done this, then we add the attributes to the data set, and a attribute table corresponding to this may appear in this manner. Having done this, we now need to do the cross check of the derived data from the acquired information from various sources like Google Earth, map.live.com, and some data may be used by the analyst to generate information regarding the validation. So, here some validation has been carried out for some buildings, and the highlighted light blue colors are those buildings for which ground information has been made available. Based on this, we create the attribute table for the ground data set, and then based on this we can now merge the information or run the software to find out what is the type of area which has been identified both from the satellite and from the ground, and compute what is the percentage error. By and large, it has been observed that the percentage error is varying between minus 5% to 1.2%, which as a matter of fact is not a very significant deviation. Having done this, now what we do is we apply both the attribute information and the data set which has been generated from the GIS, from the remote sensing information, and now we can create different information layers such as construction type. We have provided 3 different categories of construction. One is the blue, which is basically steel, the next is red is wood, and yellow is belonging to those regions for which there has been some form of vegetation activity. Next is occupancy. So, this tells us the different types of occupancy which could be there, such as commercial, commercial with retail, general commercial, or multi-family housing. So, in this particular image we find that there are four categories of building types which are present here on the basis of occupancy. Similarly, we can identify the roof covering, whether it is wood shingles or it is PVC fiber mesh with bitumen covered concrete tiles, or the third type of roofing material is concrete roof with glazed tiles. So, this tells us the different types of which building is having different type of roof covering. Furthermore, the building can be further characterized by its geometry, and this geometry could be its flat roof or it is gabled roof. So, we find that by and large the buildings are having flat roof. In this case, only some buildings at the bottom center part of the image are seen as glazed tiled roofs. Similarly, the shape configuration of the buildings, that is whether it is regular, irregular or regular rectangle, these information can be provided during the merging of the data sets. Having done this particular task, we are now able to identify the basis of the different types of building attributes which are there, and using this information we can create the database. Viewers, you will be able to appreciate that from the satellite data, informations which have been extracted are of a very varied type, and thus it highlights the utility of using such advanced techniques of surveying to create different theme based maps which are there. With this application, I come to the end of this particular course material on advanced surveying techniques. Thank you.